Right, welcome everyone again. My name is Dima Shliktenko. It's a great pleasure to welcome you to our last Green Family lecture of this series. So many of you have been here for the first lecture, so I apologize for the repetition, but still I would like to emphasize that this is a lecture organized by IPAM. It's an NSF-funded math institute on the UCLA campus. IPAM runs a lot of programs that are designed to bring together different disciplines, and there's always math at the core of it. IPAM's motto is "Math changes everything," and this lecture is part of that. There are many ways you can be involved with IPAM. I would like to reemphasize that we have our Frontier Society, which if you'd like for a small membership fee, you have various benefits. And if you're interested in that, please see one of the IPAM staff people outside of the room. The Green Family Lecture Series was established through a generous donation from Mark Green. Unfortunately, he could not be here tonight. Mark was a founding director of IPAM, and he has given a sizable donation that has enabled these lectures to start. And a more recent donation from Mark and his family allowed us to double the number of lectures, and so now we're offering 2 Green Family Lectures a year. So our next Green Family Lecture will be a Nobel Prize winner, Barry Barish, who will be speaking during our Gravitational Waves workshop in January. The last thing I want to mention is that after the conclusion of this lecture, there will be a reception, just like last time at IPAM. So there'll be a small question and answer session, and after that we can all head back and enjoy the reception. Let me introduce now Terry Tao, who'll be introducing our speaker.
Didn't actually prepare an introduction this time because I didn't realize that we'd be repeating. So I already introduced Emmanuel on Tuesday, so I guess I won't say much further, but he's going to give a second green lecture on statistical reproducibility and on the details of his knockoff framework.
Thank you very much. First of all, I'd like to thank everyone for returning to these lectures. You had a lot of me this week. It's not my fault. So what we're going to do today is it's a continuation of the first lecture where, in the first lecture we were a bit hand-waving. We talked a lot about big problems in the reproducibility of science. And I kind of outlined a framework that might actually alleviate the problems we see. And so the goal of these lectures is to just give some meat and just tell you a little bit what's under the hood and show you some stuff. Before I get started, do we have a lot of people who are not here during lecture 1? Quite a few. Okay. All right. So I hope I will not be too incomprehensible. So don't hesitate to stop me if something is not clear. But I mean, basically, we're going to build on lecture 1, so we'll see how it goes. Okay. So the problem we care about is very important in the modern sciences. In the big data era we live in, there's a response Y that we seek to understand. For example, whether you're going to get a form of cancer or not. We have lots of variables that we would like to see how they relate to this outcome. So perhaps I have all of your genotype, and the goal that everybody asks is, well, which genetic variations affect the trait, the risk of getting a disease? I want to repeat this again and again, which is it's not a predictive problem. I'm not interested in predicting your cholesterol level or your chance of getting a disease. I'm interested in understanding which genetic variations are provably in the pathway of the disease. And so from a statistical viewpoint, we have these questions that we talked about a lot last time, which is I have a response Y. This response, it's whether I have a disease or not, or it's my cholesterol level. I have lots of variables, and so there's an object, which is a distribution of Y given X. And if we think about a disease, it's very clear that most diseases do not, most genetic mutations have nothing to do with the disease. Only a few have something to do with this disease. In other words, this distribution of Y given X only depends upon a few X's, and I'd like to find them without too many false positives, right? That's what we've discussed on Monday. And so just to kind of couch this, again, we have I'm going to use examples from genetics, but they are everywhere. Which factors determine whether you're going to repair alone or not? Which gene expression profiles determine the severity of a tumor? Lots of variables. We want to understand the response, and the response depends, the conditional distribution depends on which variables. And so what we want is we want to select as many variables as possible that influence the response without too many false positives. And we talked about the false discovery rate, which is essentially the expected value of the ratio between the false positives and the number of features selected. And that's what we wish to control. Okay, everybody's with me? So far, so good. And if we don't do this, we've discussed at length what could go wrong. In fact, it's interesting that I was scanning the literature between Monday's talk and today's talk, and there were several articles relating to this in the popular press just in the last 3 days. Okay. So, mathematically, what we want to do, so I'm going to try to put a bit of math and a bit of meat into what I'm doing so that we do not stay at a superficial level. We're going to say that a variable is not of interest to me, that is, a genetic mutation is not interesting if the following is true. If it does not help predict the outcome once I know the value of the other mutations. It does not have any, it does not bring any additional information about the disease status once I know the other genetic mutations, right? So what I'm saying mathematically is I'm not interested in reporting a variable if it's conditionally independent of the outcome I'm studying, given what I already know. Does not bring new information. And so if you work in graphical models, this is the language of Markov blankets. If you have the usual Markov property that you put on graphs, then the set of non-nulls, the things that I want to report, are nothing else but the Markov, the neighbors of the node y in your graph. Okay, so we're doing things that are well motivated. And so what we talked about last time is that I think science has shifted enormously. Before, we were studying the effect of a single gene. We were making a hypothesis about a single gene, and we were designing an experiment to test a hypothesized function. And now we can measure all genes at the same time, and we can do this, and not only this, but we have like very powerful algorithms that we can run to try to extract from this data interesting information. And so, for example, I can use deep nets, I can use random forest, SVM, blah, 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 try to understand from data what's the importance of each gene, and I'm going to get a plot that looks like this, right? So maybe lots of things are set to 0, a few things are not 0, and then the things that we talked about is, should I go and take this data point, and is it a true positive? Is it large enough, then can I write my Nature or Science paper and say, this is important? Or, if I do this, if I report this guy, will this be invalidated by further studies? And so the thing that we've discussed enormously on Monday is, and I'm rehearsing what we discussed on Monday, is that we have no idea how the relationship between y and the variables, and certainly it's not linear. So we have no idea how y depends on x. We have typically in the problems we discussed on Monday, a large, high dimensionality. We have 300,000 SNPs, perhaps 5,000 individuals in our study. So we're trying to assay a lot of things. And then we produce these plots, and then we argued we have no idea about how to compute the distributions of these things. And so we're facing an important but difficult problems because all the tools we have don't seem to apply. Okay. And so the talks, the lecture on Monday was saying, okay, so we have this kind of black boxes that compute for us important scores for each gene, each SNP, each whatever. And what we're going to do is we're going to not only use this black box on the original data set, but we are going to augment the data set with fake features. And then when we run the algorithm, let's say deep learning, on both the original and the knockoffs, we're going to get 2 sets of scores. And what we're going to argue is how we can build these knockoffs so that if your null variable, if that actually your null, that is you do not influence the response, y is conditional independent of you, given everything else, that the scores that comes out of this black box let's say variable 1 is null, then the scores that come out of the black box are exchangeable. They have the same distribution. And so I can use the black box, the knockoff scores are as a negative control, as a control group to calibrate the selection procedure. Right? So what we talked about on Monday is that we get two types of scores, and the goal is to make them pairwise exchangeable. And now, once we have them to be pairwise exchangeable, right? So something like this, right? That's what we talked about. They're pairwise exchangeable. We're going to use what we see over here to inform and guess the number of false discoveries over there. Okay. All right. And so the way we do this is we get two types of scores, and we're going to combine them into a single score. So we get a score for the original variable, the thing that is physical that I've measured, and the thing that I created on the computer that is fake that I created myself. And so we get two scores. We get a score for the true variable, and we get a score for its knockoff. And what we're going to do is we're going to combine them into a single score to assess the importance of mutation J. And we're going to do this in such a way that we're going to take any function W which is anti-symmetric, such that if I were to exchange the true score and its knockoff, I would just change the sign. And what we talked about, so for example, one example might just be to look at the difference. So for those of you who do like high-dimensional models, this could be, I don't know, the regression coefficient that the lasso would give to a random variable at a cross-validated point minus the coefficient that it gives to the knockoff at the same cross-validated lambda. And now, what this is, because zj and zj wiggle are exchangeable, then these w's have random signs when they're null. Of course, when they're not null, they should be more likely to be positive, because the score of a true variable is likely going to be higher than the score of its knockoff. But when you're null, then you have a random sign. Okay, and so for those of you who do a bit of statistics, what we're doing here is we're constructing sort of what you can think of as one-bit p-values. Okay, a null variable, a null gene, a gene that has no influence on my getting the cancer or not, is equally likely to be positive or negative. Okay, and then we went through the selection process. Now we have scored all of our mutations, and they're ordered in this fashion by, so let's say this is the absolute value of W, and the selection is simply what we discussed on Monday. The selection is, I'm going to select scores that are large and positive. And so what I'm going to do is I'm going to go back, I'm going to start over here, and I'm going to come down over here, and each time I'm going to evaluate in a gray box like this all the scores that in magnitude are above t. I'm going to calculate an estimate of false discovery proportion, which is the number of minuses over the number of pluses. And I go down this way until the last time this ratio is below my target, my 10%. And okay, so this is what we do, that we discussed on Monday. And if you apply this procedure, then you have this sort of wonderful result that no matter what the relationship between y and x is, no matter the sample size, no matter the dimensionality, no matter nothing, the false discovery rate is controlled. Okay, so it looks completely non-parametric, and you achieve the target. So, okay, so why does this work? So after all, it's a series of lectures hosted by IPAM and a math department, so I thought I should give you a little bit of mathematics. These are going to be my mathy slides, and so we're going to have 3 mathy slides to see why this works. Okay, so why does this work? So what the method does, and I think it's sort of, the math is sort of pretty, so that what this works. So what I do is here, I take a point and I count the number of pluses and number of minuses, and so in that case it would be 1/5, and I'm going to move this thing away until the last time this is below the threshold. And so when it's a data-driven procedure. You see the number of the selection I'm going to make, the cutoff tau, the point I'm going to pick is random. And so when I stop, when the procedure stops, well, it's a false discovery proportion. It's going to be the null that have a score which is above tau over the number of selection that have a score above tau. Right, so that's kind of what my false discovery proportion is. And so what I'm going to do is I'm going to just show you why the false discovery rate is controlled when you apply this strategy. I'm going to try to, I'm going to wave my hands a bit, but hopefully you'll get the spirit of this. So the false discovery proportion is the number of null that I'm reporting over the number of events that I'm reporting. And so, of course, I can multiply this by this something and the same thing. And so, of course, I do not change this ratio when I do this. And then I highlight something in blue over here. When the methods stop, by design, this ratio is less than your target. It's less than 10%. It's less than 0.1, because this is how I choose tau. And so this blue thing is what I control, actually. So this has to be less than tau. Q, my target. And so what I'm left with when I'm stopping, there's a random time, and when I took probability in my youth, what do we do with martingales? We stop them, that they all, and so that's what we're going to do. So when we stop, the false discovery proportion is going to be less than Q, because this ratio by design, this is how I designed the procedure, is less than Q, times what? Well, times the number of pluses over 1 plus the number of minuses, okay, for the nulls. But now you see why the method sort of works. This method sort of works because, well, this ratio, what is it roughly? What? It's roughly 1. And why is it, Terry, that it's roughly 1? Because they are coin flips. So when I flip coins, the number of pluses is roughly equal to the number of minuses. So this ratio is 1, and therefore the false discovery rate is roughly Q, or at most Q. But of course, I stop at a random time, so I have to be a bit careful. And so what I have to show is when the method stops, so I'm going to change this. This is the number of coin flips that are positive, the number of coin flips that are negative. I need to show that this ratio is less than 1. Okay, so let's do that. Okay, so that's where we're going to invoke martingales. And so what it is that there is this process, which is a number of pluses to the right of t over the number of minuses to the right of t. And what I claim is v plus over 1 plus v minus is essentially a martingale with respect to, so you see, you start from 0, and you're going to move this way, and each time I reveal whether you pass a minus or a plus, and so your filtration is how many pluses and minuses are left to the right of t. Okay, so you're at capital T, and so at capital T, you know how many pluses are left and how many minuses are left. And then I say, can you predict the process later on at time s? Can you predict it over here? Okay, and so I say, can you actually calculate the expected value of the process over here given what you know up to time t? But now you say it's very easy because, that's kind of going back to when I was a child in probability, which is, well, these things that receive plus and minuses, they're like black balls and white balls in an urn. And so I'm going to advance to this. And so if I knew that there are 4 balls left and that there were 3 black balls and 4 white balls, I can calculate the odds of having any number of white balls over here. And so just to put some math behind this, what I'm going to do is I'm going to advance to time s and condition on the number of statistics that are still in magnitude above s, let's say they're m, and obviously the number of condition on the number of events left, then this has to be hypergeometric. And so now we know the distribution of these things, and we can actually calculate the expected value of this hypergeometric thing, and it's less than this. And so what that is showing is that this process is non-increasing in time. And when I have a process that is non-increasing in time, I can stop it at a random time. And so what I can show is that the false discovery rate is less than Q times the expected value of the number when I stop, but that is no more than the same thing at the beginning, but at the beginning I can do the calculations because I see binomials. And so it's less than Q. And so this is sort of mathematically why this whole thing controls the false discovery rate. Okay. All right, so now the rest of the lectures will be a bit less formal, and so we're going to see how we can build knockoffs. Okay, so to build knockoffs and to create this, to make sure that my black box gives exchangeable scores when it actually tries to compute whether a variable is in the model or not, we can assume that we've got samples from x, y. I'm going to assume to build knockoffs that I know something about the distribution of x, but I know nothing about the distribution of y given x. And the way this is done is what we sort of discussed on Monday a bit. The way I do this is I say, okay, so you give me a random vector, x1 to xp, these are my genes, and then I need to create fake genes over here in such a way that, and I think that's the example I used on Monday, this is my mutation over here, and this is a fake mutation, and if I were to swap what the computer imputed with a true mutation, I would not change the distribution. If I do this, it's not very hard to see that when you feed this to a black box, the score, no matter what you want to compute, as long as you treat knockoffs and original variables symmetrically, any score you want to compute will have the exchangeability property. So the machine will work. And so the goal is to make this. And so this is a cute question in probability, or in applied probability, or whatever, or machine learning, whatever you want to call this. I give you a family of random variables, and you need to extend it in such a way that you can swap them. And we're going to see how we can do this. Okay. So there are two problems with this method. To do this, I need to be able to know the distribution of P of x, which is not always realistic in practice. And even if I knew it, I would need to be able to do something like this algorithmic. So there are two questions that are fundamental, that if we want this program to work, what if we know P of x only approximately? And how do we make knockoffs? So I'm going to quickly discuss the first issue, which is what if I only P of x approximately? Okay, so this is work with Rina Barber and Richard Samworth, and I'm going to be a bit quick on this part because I want to spend most of my time on algorithms. But let's talk about robustness for a second. First of all, empirically, what do we see? Okay, so here you see 2 points. On the left, we're going to see power. So you know what power is in statistics? It's a fraction of true signals I'm going to discover. So here there are about 50 non-zero, there are 50 variables in my model. I want to discover them. And here I use the knockoff method using the true distribution. I use the exact covariance matrix. And I have two figures that I'm reporting here. I'm reporting the power. What that means is that basically I discovered 80% of all there was to discover. And my false discovery rate is 10%. And what's remarkable here is it's exactly 10%. It's not 5%, it's not 12%, it's 10%. So here we have false discovery rate, which is at 10%, bounded by 10%. It's a theorem, but that's what we see numerically. It's 10%. And here we see how well we do. You might want to think about this as almost the converse of the false negative rate. It's a power. It's our ability to detect stuff, interesting stuff. And that's when I use the exact model. And now for those of you who know a bit of statistics, what I'm going to do is, instead of doing this, I'm going to estimate the covariance matrix from data in sample using the graphical lasso. And what happens? The power doesn't change. So now I'm not using the true model. I'm just estimating the covariance matrix from using the graphical lasso from data only. The power is unchanged, the FDR is unchanged. Now we're going to do this. Here is another estimate of covariance matrix where it's going to be half of the true plus half of the empirical covariance matrix. And what we see, the power is almost unchanged, the FDR is almost unchanged. And now you can see that these estimates are not very good in the Frobenius. So this is essentially the relative error of sigma hat minus sigma over sigma. It's a relative error of sigma in the Frobenius norm. So we're not very close to sigma, but the power doesn't change, the FDR doesn't change. And then we become more and more empirically driven. That is, we're going to use the empirical covariance matrix more. So now the power goes down, the FDR is still the same. And as I weight the algorithm, I'm using the data more and more to learn the covariance matrix. My estimate is less good, but what we see is this, which is that what you do is you take a performance hit, but you do not violate FDR control. You become too conservative, but you don't become what we don't want to see, like you start making discoveries left and right. Now, we've tried to analyze this with Rena and Richard, and what we have is we have a way of thinking about this, which is the distribution of the feature is X, but the algorithm is going to pretend that it's Q. So I'm going to construct knockoffs that are exchangeable, not according to P, but according to Q. Right? And so if X was actually distributed from Q, then I would do what I want to do, but I'm not distributing from Q. So they're not exchangeable with respect to P, but they're exchangeable with respect to Q. And now this creates difficulties, because now the beautiful picture is a bit somewhat messed up. Now I have things like this. They're not exchangeable with respect to P with Q, which means that these kind of coin flips, they're not really coin flips anymore. They might be a bit biased, they might be a bit correlated, and so on and so forth. And it makes the analysis very, very difficult. And so the pretty picture then sort of collapses. But it can be rescued with a lot of mathematical analysis. And so basically, maybe I'll just go through this quickly. What you can do is you can say, well, you can try to measure how far Q is from P. That is, what this is trying to do is this is a measure of, can you tell that Xj and Xj are in this order? Or can you tell that they are swapped? And you're measuring the KL divergence between this and this. And what the main result says is that if the KL divergence is small, that is, you build a good knockoff, they're very hard to distinguish from their original, from true knockoffs, then the FDR will be almost controlled. And so what you see is you see a slight inflation on the FDR, which depends only on the distance to exchangeability, so to speak. And so when you are not too far from exchangeability, you may have a little bit of an increase in FDR, but it's very mild. Okay, so this part is a bit technical. Maybe I don't want to go too much into it, but I'm bringing it up to show you that there is things that says that even if I don't know the distribution exactly, things will degrade pretty gracefully. Okay, any questions about this? All right. Okay, so now we're going to make knockoffs. So we know that we have a method which is fairly robust, and now we need algorithms to generate knockoffs. So we're going to see several examples, and we're going to start with the easiest thing. We're going to make them for Gaussian variables. Then we're going to make them for graphical models, and in the end, I'm going to try to be a bit modern, and we're using deep learning to build knockoffs, and then we'll see how that goes. Okay. So let's start with simple things. Let's make Gaussian knockoffs. So let's assume that the distribution of X is Gaussian. Then how do I make knockoffs? Well, that's not going to be difficult. Remember that what I want is that if I take original variables and knockoffs, when I swap them, I don't change the distribution. Okay, that's what we want to do. In particular, this means that the knockoffs, X wiggle, marginally need to have the same distribution as X, so they need to be also Gaussian. So let's make Gaussian knockoffs, and you'll see it's very easy. So let's say X is normal with mean mu and covariance sigma. My proposal is to build knockoffs in such a way that they're jointly Gaussian. So we're going to build knockoffs so that jointly X wiggle is Gaussian, so it has a mean and it has a covariance. And what I say was, it's not difficult to see that, well, X wiggle needs to be exactly like this. So X wiggle needs to have mean mu and covariance sigma. And so the mean has to be, well, mu, because X wiggle needs the same mean as X. The covariance of X wiggle is sigma. So this is the covariance in block form. The covariance of X is sigma. The covariance of X wiggle is sigma. And what do we need off diagonal? What we need off diagonal is that the covariance between a true variable and a knockoff is the same as the covariance between two true variables, except for a variable and its knockoff. And so off diagonal, you have sigma, you can subtract anything you want on the diagonal, and this will do this. That you can see that if you swap variables, then you will not change the distribution. And you will not change the distribution because what does it mean to swap variables? It means that you're going to perform a row swap and a column change, and that does not change this thing. And of course, that doesn't change this. And so that will do what you want. Of course, there's a little catch, and the little catch is that this, you need to choose an S, so that this must be a covariance matrix, so this big matrix must be positive semi-definite. What you do? Well, I give you mu, I give you sigma, or you estimate this from data, and then you're going to generate an S so that this is positive semi-definite. You have the joint distribution, therefore you have the conditional, you sample from the conditional, using the regression formula that we teach in Stats 101 or something like that. Given X, you sample X wiggle from given X, which is conditional normal, you use the regression formula, and that's what you do. Now you must have a question now, which is what? No, it does not relate to Y, because that's how we build knockoffs. We build knockoffs so that they're conditionally independent of Y, so that they are real nulls, so that I can use them as a control groups. Then it's like, what is S? And a lot of you asked me this question in the last 3 days. Why don't I just do X wiggle equals X? Okay, X wiggle equals X would be perfectly exchangeable, but that's a bad choice. And that's a bad choice because I'm going to get the same statistics, so I cannot make any discoveries. So I want to make X wiggle as independent of X as possible. In other words, you see, what I see on the diagonal is a covariance between X1 and X1 wiggle. I want to make this small. I want X1 to point in one direction. I want X1 wiggle to point in a completely different direction so that I can actually get power and detect stuff. And so that's where optimization comes in. So I need to do this, but I don't want to get exact copies. I want to get things that are quite different. And so the way we're going to choose S is by optimization. We're going to try to make variables and knockoffs as different as possible. There are many things we could do here. And I think on Monday we discussed the possibility of minimizing the mutual information between X wiggle and X, which we could do. We do something else. We maximize the sum of Sj. That is, we try to make X and X wiggle as orthogonal as possible, subject to this matrix being positive semi-definite. No, I don't think so, no. Because the mutual information has a log det of something. I don't think it's exactly the same thing. In fact, I tried both on the computer. It's not the same answer. So, no, it's not. It's not exactly the same thing. Like, what do I cross-validate exactly? What I'm trying to do here is I'm trying to make, you see there's the X space. I'm going to try to put X wiggle in a space as orthogonal to the X space as possible so that I can see signals when there is signal. So when there is signal, when Y is pointing in the direction of X, if X wiggle were like this, it would be terrible. So I'm going to try to put it over here. That's what this is trying to do. Okay, so that's one way to build knockoffs for Gaussian variables. Okay. Now, when you do this, so maybe you can do power curves, and you can do, and so the black curves, again, this is my power FDR plots, and this is as a function of now we have an X matrix, and when we go from left to right, the correlation between the columns of X becomes more and more strong, so the variables becomes more and more correlated. And so in black, you see the power of the knockoff methods, and of course the power goes down as correlation increases because it becomes very difficult to tell variables apart when they get super correlated. The resolution is not in the data, and we see what the theorem says is that FDR is controlled at the 10% level. And so you see, we're trying other methods, but these other methods, they don't control the FDR because it's a problem that is extremely difficult. And so here is again, the black curve is a knockoffs method. Now it's here, we're pumping up the coefficient amplitude, the signal strength, if you will. And we see that as the signal strength increases, the power of the knockoffs increase, and the FDR is spot on 10%. And other method that we tried, well, they don't control the FDR because they don't know how to construct p-values and things like that. Okay, we can do it for logistic regression. We see the power. Again, as the columns, the variables become more and more correlated. Of course, the power decreases because the features become hard to tell apart, but the FDR is, we tried other methods proposed in the literature, but they don't control the FDR because nobody knows how to do this in the problems we're looking at. Okay. Now, one thing that people ask me a lot is, what if you had a good prior model for your model, and what if you were Bayesian? And what I'm trying to say here is that if you're Bayesian, use all your prior insight into designing a good test statistic, a good W, a good Z. And so here we're going to use, if you're Bayesian and you have some ideas about what the coefficients or the variables you're looking for might be, then you might actually encode this into W itself by, let's say, Z is a posterior given the data. And the prior doesn't have to be correct. The MCMC algorithm doesn't have to converge. Nothing has to happen. FDR is controlled. That's a theorem. But what happens is if you have a good Bayes model, then the power will go up. And so here we see two methods, one based on the statistics, one based on a sort of Bayes model. FDR is at the same level for both of them, but one has more power because it's a bit more informed about what it needs to do. And so what I'm trying to say here is that you have enormous freedom in how you're going to design your feature important statistics. Do anything you want as long as you trace original variable and knockoff symmetrically, the false discovery rate will be controlled. Okay. So if you, in particular, if you have a good Bayes model in mind, just use it. By all means, use it. And don't even wait that your MCMC algorithm has converged, because the FDR control guarantees are independent of convergence rates or anything, because as your MCMC algorithm will treat variables symmetrically, that's all you need. Okay. Okay. So after Gaussian, we need to extend to graphical models. And so that's what we've been doing with Sabati and Cesia. So Sabati is very dear to me. She's my wife. Matteo Cesia is a wonderful student at Stanford. So I'm working with Italians on this one. So here's one thing that is interesting. And you can think about this as an abstract problem that I find interesting. I mean, I'm really interested in, I give you a distribution, how would you make knockoffs? It's a kind of cool math question, I think. I mean, math is cool, and it's a cool math question. Here's P of X. Theory gives me P of X. I have to create P of X, X wiggle, so that I have to create an algorithm for making them. And what we found with Jianqing, Yingying, Lucas, and Jinqi, we found a simple algorithm that just does this. And the algorithm is very simple. Very, very simple. It's totally unpractical, but conceptually it's simple. So let's show you how it works. It's a sequential algorithm where you're going to just generate knockoffs one at a time. Okay. And the fact that it works is not completely trivial. I mean, it will take you probably 2 hours to figure out, but it's not immediate that it works. But here's how you do it. So let's say we have 3 variables. So you give me x1, x2, x3. I need to make x wiggle 1, x wiggle 2, x wiggle 3. So what do I do? Well, I'm going to make a knockoff for variable x1 by resampling x1 from the distribution of x1 condition. So minus means it's all variables but variable 1. So I'm going to generate x wiggle 1 from the law of x1 given everything else. And now I'm holding knockoff number 1. Is it exchangeable with x1 given what I know? Yes, it's actually conditionally independent of x1. So it's actually better than being exchangeable. Once I have this, I've got the law of x and x1 wiggle. And now I need to make the second knockoffs, and that's where it gets a bit tricky. I'm going to sample x2 from the law of x2 given all the other variables and x1 wiggle. And now I've got x1, x2, x3, x1 wiggle, x2 wiggle. I've built my first two knockoffs. And now I know the distribution of x and the first two knockoffs. And I think you see where this is going. Now I need to make the last one. And how do I do this? I'm going to sample x3 wiggle from the distribution of x3, given the others and the first two. And my claim is that it does the job. This is actually creating a perfectly valid knockoff. The distribution, the joint distribution at the end, is exchangeable. I can swap anything, it doesn't matter. Okay, so it's not trivial. I can see Terry doing some calculations already. What I've learned working with Terry is what takes you 2 hours takes Terry 20 seconds on average. So the 20 minutes may not apply to everyone, the 2 hours may not apply to everyone. Okay, so this is exchangeable. Now, is this an algorithm? No. It's completely impractical. Because I'm going to have to recompute this damn normalizing constant that those of you who do physics, you know about. I have to recompute each time this normalizing constant. It's impossible. So this is, if you want, this is an existence proof. But it is not an algorithm. It's too abstract. Except if it's a Markov chain. If X is a Markov chain, then I can deploy this, and I claim that everything becomes extremely efficient. So a Markov chain, we all know what that is. I mean, we don't need to introduce Markov chains, I think. And the knockoffs procedure, knockoffs to produce knockoffs for Markov chains is essentially trivial. You go through this abstract procedure, but what you realize is that everything cancels out. And so you can go and generate knockoffs or Markov chain in a single pass in linear time. That is, it takes time equal to the length of the thing. That's it. So to generate knockoff, well, we're going to start with the first one, and I need to resample x1 condition. So x1 is from the distribution of this given the rest, but it only depends on x2. So it's very easy to get this guy. And then I need to get this guy. And so I need to sample x2 wiggle from the distribution of x1 given the rest. But given the rest, you know, all the information is only in the future and the immediate point. And so it depends only on this guy and these three guys. And then I need to get the next one. And you get the picture. And the point is that there's a nice recursion formula for the normalizing constant so that everything is extremely streamlined, extremely efficient. It's extremely fast to generate knockoffs when you have a Markov chain. And so you have a linear time algorithm to do those. It's very, very easy to build knockoffs for Markov chains. Okay, so let's try to add a bit of complexity now. What's more complicated than a Markov chain, a model that is used a lot? Hidden Markov models. So let's build knockoffs for hidden Markov models. People know what is a hidden Markov model? Sort of. A hidden Markov model is something like this. There is a hidden state, which is a latent variable, if you want, which is a Markov chain. Okay, and that's the Markov chain. That's the latent space of the, but that's not what you observe. This is unobserved. When you're in state H1, you have an emission probability that generates X1, whereas the distribution of X1 depends on the state you're in. And so a hidden Markov model looks something like this. We have a Markov chain, and then given that we're in state H, the distribution of Xj does only depend on the current state and has an emission probability that is known. And so that's what it is. We have Markov chain generating latent variables and then emission probabilities to generate observations. And we care a lot about these models. We care a lot about these models, these hidden Markov models, because they're used to model a lot of distributions of variables. Okay, so here the H variables are latent and only the X variables are observed. And that's what I try to mention on Monday. Why is it do we care about hidden Markov models? Because they're extremely powerful to model correlations between your SNPs. So it is very obvious that if I take two mutations on my genome that happen to be close by, they're extremely correlated. And why is that? Because they co-herited. But if the thing starts to move far away, they start to be almost independent because there's been a lot of recombination in between. And so these hidden Markov models have been used with great, great success in genetics to model what geneticists call linkage disequilibrium. That is, the correlations between nearby SNPs. And this, I've talked about this on Monday a little bit. So there's enormous work where people have shown that you could improve the power of detection algorithms by imputing SNPs that you have not measured using this model, that you could impute missing data, that you could actually try to recover a haplotype from the genotype and so on. There's an extensive literature, a beautiful literature in genetics that uses these hidden Markov models to do lots of good things. And so what we're suggesting here is to repurpose these hidden Markov models to generate knockoffs. So these models are very accurate, describe very accurately the joint distribution of SNPs. So we're going to use them to build knockoffs. Since I know how to make, well, I've not told you how I can build knockoffs for hidden Markov models, but if I knew how to do this, then I could leverage this enormous piece of literature of using these models to generate knockoffs. So it became important for us to know how to build knockoffs for hidden Markov models. And that is not too complicated either. So how do I make knockoffs for hidden Markov models? So what I see is I see my genome over here. And it follows a hidden Markov model. And the algorithm will operate in 3 steps. It's actually it operates in 3 steps. And the first step is to sample the latent variable given x. So step 1, I'm going to generate from I'm going to try to sample the hidden states conditional on what I've observed. Can I do this efficiently? Is it possible in a hidden Markov model to sample hidden states given observed values? Yeah, no, maybe. Is it possible to get the most likely states given hidden observed values? Yes, what would I use? Viterbi, absolutely. So to get the most likely state, I would use Viterbi algorithm, dynamic programming essentially. But what I'm saying is I can repurpose again the Viterbi algorithm, not to get the most likely, but to get a state. And for those of you who know this, you have a forward and a backward pass. So you're going to go one way and then the other, and you get a sample from the posterior of h given x. It's a variant of Viterbi. Well, now we have a Markov chain, so we know how to make knockoff with that. That's not difficult. This is what was before. And now that I have this, how do I generate knockoffs? I sample some emission probabilities, and that's it. And that's a perfectly knockoff copy. It's perfect knockoff copy. In fact, it's more than this, that this jointly is a knockoff copy for this. But in particular, this and this are pairwise exchangeable. So I know how to make knockoffs for genetics, which is good. And of course, in practice, I'm going to have to estimate parameters. And so this is a question of robustness. Do I get the parameters right? Are people familiar with box plots? You know what these are, these box plots? Sort of, okay, maybe I'll skip box plots but what I want to say is that look at these plots. This is power, this is FDR, my target is 10%. And so this is if I knew the right hidden Markov model. And so what we see is a theorem that, well, the FDR is below 10% and the power increases as the signal gets stronger. Now I don't know the right HMM model, I'm just going to estimate the parameters from data. All I'm asking you is to see how the plots change. Because I don't really know, nobody has given me the right parameters. I'm going to just use the data to estimate the parameters and use the method on the parameters I estimate from data, get something like that. And that's a robustness once again, which is, yeah, the FDR is almost untouched. The power is almost untouched. Okay, so what we're doing then is that we're in business then to apply this to genetics. And so, as I mentioned before, we analyze 2 data sets. One aimed at understanding which mutations have something to do with the Crohn's disease, and another is to try to understand which mutations have something to do with your cholesterol level, both the good and the bad cholesterol. And in each of these examples, again, we're in settings where the number of subjects is small, it's 5,000. The number of variables I'm trying to assay at once is 300,000, a lot of things. And I think I did not mention this, but this is a data set that is dear to UCLA's heart, because this was actually collected by Leena Peltonen and her husband. And Leena Peltonen was actually of Finnish origin, and she's behind the collection of this data set. And she was a chair of the human genetics department here at UCLA for many years, and unfortunately she passed away very early. Okay, the first data set comes from Britain. It's a Wellcome Trust case control consortium. So what we have is, of course, we're not the first one to look at this data, and people have made, in original papers, some discoveries of mutations that are supposedly related to the phenotypes we're looking at. In the original data set studying the Crohn disease, 9 discoveries were reported. For the lipids, there were about 5. When we apply the knockoff methodology with these HMM models, we make many more. And so it's interesting to understand what is it that we discover that was missed in these first publications. Well, it's possible that some of these false discoveries are false, and that's a rule of the game. False discovery rate says 10% of your false discoveries may be false. So out of these 10, maybe 1 is false. Out of these 23, maybe 2 are false. That's the game. There's no science without following false leads. So, but they made a number of discoveries. You see that the power is remarkably increased. So some of them might be false discoveries, but it is likely that many of these correspond to true discoveries. And in fact, we've done a lot of meta-analysis to actually discover in these discoveries that were not originally reported, have they been reported elsewhere? And so that's what I mentioned on Monday, which is that since these original papers, people have collected, it becomes easier to genotype people have collected bigger data sets, and so there's been a lot of studies about Crohn's disease and lipids. And what we have found is that a lot of things that were discovered have been confirmed in later studies with bigger sample size, hence larger power. And so there's an excellent agreement between what we have seen published in the literature based on much larger studies and what the knockoffs framework is able to discover on a relatively small data set. Okay. All right, and so this, when you see a yes, this is confirmed in Wheeler, this is a meta-analysis pulling together lots of studies about this cholesterol, for example. I think this is HDL. And so all what knockoffs found has been confirmed in much bigger studies, which is reassuring, indicating, again, a form of reproducibility. Now, when you do things, there are lots of, when you do real data analysis, and we spend 2 years of our lives doing real data analysis, of course, there are lots of things I need to discuss, how it's implemented, how it's done, but maybe it's best to discuss this offline. In particular, there's one thing that you need to be a bit careful, which is that when you're densely typing the genome, SNPs may be highly correlated. So you might have in your data set SNPs whose correlation is 0.95. And there is no resolution in the data that will actually distinguish between something here and something here. So what we do, and I want to emphasize this, is we're going to say, all right, well, you're asking me to solve a question for which you don't have resolution. So we're going to bring the question at a lower resolution. We're going to cluster these SNPs into groups that are highly correlated, and we're going to reformulate the question, and the hypothesis we're testing now is there any signal in these clusters? And then we're going to use the same method. Okay. All right. So maybe I'll skip this. And what's nice about this method is the method, as you see, is robust. It doesn't matter how y depends on x. The method is robust. The FDR is controlled no matter how y depends on x. So I think the only thing you do when you did analysis is did I build good knockoffs? Are my x wiggle good enough? And that you can do diagnostics. That is, here's the kind of plots I've shown before. So here's the reason I believe these results is for the following reason. Here is actually a real data set, and it's actually the real statistics I'm computing, except I manufactured the Y, so I know the ground truth. I know the method is robust to Y. That I know. And so what I can do is I can manufacture a Y, compute my statistics, I know who is in the model and who is not, and so therefore I expect to see a form of exchangeability. If I build by knockoffs, I will not see exchangeability. So I can make these sort of diagnostic plots. These are the variables, the true variables that are not in the model. These are the knockoffs. And I can see that they're sort of exchangeable. The levels seem to match. I would be terribly concerned if this cloud were pushed down. Then I would say something is wrong. I need to build better knockoffs. This is not working. But I can do these plots. And it's a bit, for those of you who do statistics, a bit of different, like when you do linear models and P is 300,000, you have 300,000 variables, how do you do model checking? But I'm not sure. But here you can sort of do model checking. You can, you give me SNPs, I can hold out SNPs, I can use my model to impute them, I can see if I do a good job. Or I can do things like this. I can check whether what I'm doing is reasonable. Okay. All right. It's important to be modern. That's what I learned by coming to IPAM every year. I have to be modern. And so how can I not think about deep knockoffs? And so this is Joy, who is other Italians. Romano is not Italian. Romano is from Israel. He's from the Ternion and Matteo Sesia. And now what we want to do, and maybe call me crazy, you have the right to call me crazy. So suppose you don't have a model for P of X because I don't have this marginalist who told me that, yeah, there's this beautiful HMM, they work so well. So I don't have a model. Can I use what we've learned in deep learning in probabilistic model to actually build knockoffs on the fly? And that's what we're doing. And so the idea is to leverage, and more than leverage, is to repurpose what we've learned from generative modeling techniques to construct knockoffs. Don't care about distinguishing a cow from a cat or a cat from a panther. I don't really care. I care about science, and I care about can I trust what I'm finding? Can I publish it? Can actually NIH invest dollars into studying this gene or not? And so what we want to do is we want to use essentially GANs to build knockoffs. It sounds strange, but that's what we want to do. So how are we going to do this? Suppose I have a trained neural network, f of theta. So a trained neural network, this is very abstract. This is saying that basically you have a way that generates samples. You take a z, which is some Gaussian stuff. It goes through this incredibly complicated f theta. It generates a sample x. That's your generative model. What we want is we want to use this network to draw knockoffs. Of course, these knockoffs have to depend on the true variable, on my SNPs, and some random things, but I want to use a network to draw knockoffs. And now what I need to do, what I'm going to do is I'm going to train a network in such a way that it becomes very hard for you to distinguish between a true variable and a knockoff. So we're going to do this by minimizing on real data an empirical function that's going to do two things. This is going to measure the distance to exchangeability. It's going to be 0 if when I swap, I don't change the distribution. It's going to be the empirical version of this. This term is here to do what? I don't want x and x wiggle to be the same. So I want to be exchangeable. At the same time, I don't want to be too much alike. So I'm going to try you give me a lot of data, I'm going to write down an objective function that measures distance to exchangeability, and at the same time is generating knockoffs that are not like the original ones. Now let's look at each of these terms. The first term is going to be measuring the discrepancy between two distributions from sample data. We've tried a lot of things. We've burned, I don't know how many months of GPU power And eventually we settled on this beautiful idea of maximum mean discrepancy, MMMD method of Shortcut and so on, where RD is going to be based on MMD playing the kernel trick where we do these things. And the first term is also enforcing that the covariance structure is what you expect. So basically, this first term is an empirical term that measures distance to exchangeability. And it's using how it measures distance using MMD. The second term promotes small correlations as much as we can between variables and knockoffs. Now, I've trained a network, I observe this. Now, this may not be good enough. So what I'm going to do is I'm going to perform gradient descent until I've got something that is good. And so, of course, we're going to update the training network. We take a gradient step, and we're going to update theta until we're happy with this. Now, here are some plots that are a bit surprising. What we did, so we did this. This is like purely data-driven. It's Emmanuel being so scared that he's not living in the right century. And we fed this with Gaussian data. And then we saw what the network is going to generate. Okay, so we fed this with an autoregressive process of order 1. These are the Gaussian knockoffs. This I use the kind of the formulas I gave you at the beginning. And this is what the deep network returns. It generates Gaussian knockoffs. Okay? And so here is interesting, because here you see the correlations between, so this is what you would do if you were to use a Gaussian formula I gave you. This is a Gaussian knockoff. This is a covariance between yourself and between xi and xi. This is a covariance between xi and this neighbor. It's an autoregressive process with rho equals 0.5, so it should be 0.5, which is what you see, then 0.25, then powers of 2. And so you see the covariance structure of your Gaussian process. And what the deep network returns something very, very similar. Return things that are marginally Gaussian with the right covariance. And so we can even look at more things. That is, we can look at the SDP construction. And so what you see here is the SDP construction is this value of S. This is indicating the correlation between yourself and your knockoffs, and they're concentrated over here. For the deep network, the deep net is actually, it's a bit wider. It's not as good as this, but it's pretty good. It's creating knockoffs that are decorrelated with yourself that seem to have all the right properties. So we're happy with this. But of course, it's work in progress. I took too much of your time already. I thank you for coming these 3 days, and I'll see you at the party.
Are there any questions? That was a pretty big optimization you were doing just there.
Yeah. We're burning some GPU. You see, there's one thing I ask my students sometimes, is like, can we actually put a sticker on these plots to show me energy consumption? This is not a green plot. We do SGD. We do SGD. But we build these knockoffs, so we fiddled around with this quite a bit. What's the right measure of discrepancy? Is this a KL? Is this something else? In the end, we were very happy with MMD, for those of you who know what that is. And then there are several twists, and then we train the network until this cost function is small. Yes?
You mentioned using the Markov model where the xi are the genes observed.
The genotypes.
The genotypes.
Yes.
Is there a natural ordering in that sense where you have like x1, x2, x3?
Of course, of course. I mean, this is literally going along the genome. Right, so you see, the way they think about this is like, this is, you know, this is a latent variable, this is a person. And so this is the beginning of chromosome 1. Of course, the chromosomes are independent because each time you get a random pair from your parents. So they're independent, the chromosomes. But on a single chromosome, this is a latent variable, as you can see. And I'm at the beginning of chromosome 1, and that's you. And this is, you know, here you're of this sort of ancestry. I mean, I don't have the right to say these things, but if you see what I'm saying is, this sort of is your ancestry at this location, then there was a recombination, and it is a sort of your ancestry over here. This is a different person in the room. His ancestry is more like European, Asian, you know. I don't have the right to say these things. This is purely phenomenological, but this is ordering. This is actually locations on the genome. And the correlation between SNPs is actually depending on the number of base pairs that you have to go from one point to the other. So it's actually very perfectly ordered.
For the GWAS results, how much does your method affect the ranking of the SNPs versus where you draw the threshold?
Well, I mean, what we get is, at the end of the day, with the knockoff technology, we get something like this, right? We get test statistics that have a certain value, and this is our ranks. And what we need to say is, how far down this list can we go until we believe that we can no longer guarantee the reproducibility of our findings?
You're using the exact same ranking.
Yeah. Well, no, the ranking will depend on which test statistic you use. And that's what's very interesting about this, which is that this is a machine. And the machine is going to be as good as what test statistic you want to use. So, for example, let me tell you what we did for the Crohn's disease. For the Crohn's disease, we scored variable as follows. We looked at the regression coefficient in an L1 regularized logistic model, and we looked at the amplitude of the lasso coefficient, so to speak, at a lambda, which we got by cross-validation. So for us, we measured the importance of variable by looking at the size in a lasso model of the regression coefficient at the lambda that has been cross-validated. And then we subtracted the coefficient for its knockoff. That's what you see. That's what, that's, oops. Whatever I have got, yeah, that's stuff. So a big value of W means you got a big coefficient and you were much larger than your knockoff friend.
I mean, like a follow-up question would be then if you sort of compared from the original study, the SNPs did an equivalent number as you're doing.
I see.
They replicated the
I see.
rate.
Yeah, I think what we find so you're asking for a final question, which is when we look at the ordered list and the p-values, do we see some correlation? Yes, we do. But we find stuff that were missed by the original study. In particular, there's some things that are interesting, like we seem to have more resolution. Like, because they do marginal testing, they tend to lump a lot of things together, but sometimes we can say, no, there's something here, and they're not the same. So for example, sometimes we can get two discoveries in a clump. And so we see different things.
Other questions?
Of what? Oh, in the deep knockoffs, we have several layers. We have at least 20 layers. Okay, so here we have in these examples that I've shown you. So let's look at the deep knockoff. We're in a favorable regime where the number of samples we have n is about 20 times the number of variables. So we have quite a bit of data to learn. Yes.
Say the deep knockoff model for treating genotypes as poorly over rare variants. Are those going to show up more in your false positives?
It's possible. It's possible. So I don't know about this. Rare variants, I can't say too much yet. Yeah. What we're doing with rare variants, since when we have very rare variants, we just remove them from the data because we don't really know how to treat them at the moment.
Let's say if the test statistic you use just depends on the correlation or partial correlation, can I relax your assumption on this
It's a very good question. It's a very good question. I think.
I don't need to care about it, get about the model, whatever. I just need a sample to learn.
I don't know. I mean, you need to make sure that your statistic zj and zj wiggle are exchangeable, and it's going to be more than the second moment.
Right.
Because
But in practice,
if they were Gaussian, that would be the second moment, but they will not be Gaussian. They will only be approximately Gaussian by the central limit theorem. So you need a bit more. But you're right.
practically, it's probably enough to make sure that.
Yes. Okay, excellent question again. It depends on which statistics you use. So if you use statistics that you really use at extreme values of a few things, it's not enough. But if you use things on logistic regression, lasso stuff, yes. By matching the first two moments, it's good enough. You're absolutely right. Absolutely right. Matching the first two moments for practical purposes is good enough, unless you have a statistic that is a bit devilish, and it's going to start to look far out in details for anomalies, and then that might not be good enough.
All right, so unless there are any further questions, let's thank Emmanuel.